Hi guys, in this video we're going to take a look at projectile motion. Before we begin, it's important that you are able to recall how to decompose vectors into components, how to add vectors together to find the resultant vector, and how to use motion equations to calculate the motion of a particle or object in one dimension with constant acceleration. Projectile motion describes the motion of a particle or object in two dimensions acting under the effect of a constant acceleration such as gravity. Let's consider two identical objects. The first is thrown directly up, so it travels upwards, slows down, stops, and falls back down again. The second object is thrown with an initial velocity at an angle, and so it comes up, slows down, and then falls back down again towards the ground. What happens as that object moves up, though, is similar to the first case. Initially, it has this initial velocity, which could be considered to be two components. One up, which we'll call u vertical, and one to the side, u horizontal. As the object rises into the air, its horizontal velocity remains unchanged because acceleration in this case is gravity acting down. There is no acceleration side to side. So the velocity of the object up has slowed considerably, and that's now the overall velocity of the object. Up here, we have the same thing in terms of the horizontal velocity is unchanged, but now its vertical velocity is quite small, meaning its overall velocity is in that direction. At the very top, while it still has its same horizontal velocity, there is no longer any vertical velocity at all. It's momentarily stopped in the vertical direction. And when it comes back down, it does the opposite. We continue to have the same horizontal velocity, but it now has a small downwards vertical velocity. And as we go further down, horizontal stays the same, vertical continues to get larger in the negative direction. So the important points to take away from this are that there's two different things happening in the different dimensions. Horizontally, the speed is remaining unchanged as there is no acceleration. Vertically, the object is slowing down, stopping, and beginning to move in the negative direction, so downwards, at an increasing speed. That's exactly what happens in our first case. So we see that we can collapse this problem into two separate problems, one involving the horizontal motion, which is constant, and one involving the vertical motion, which follows exactly the same rules that we've already applied to throwing an object directly up. And this is the really important point. Motion in each direction can be considered separately. Yes, the two have something to do with one another. It is the motion of a single object. But in terms of the mathematics, we can separate it into the vertical motion and the horizontal motion separately. To show exactly what we mean, let's step through the motion of those two objects again, bit by bit. So at first, this object has an initial velocity directly upwards, and this object is going to have the same vertical velocity such that u equals uv for those two cases. The difference is that this second one is also going to have a horizontal component to its velocity. So we go to the first one and we follow it for the first few seconds of its motion. In that time, it rises up a certain distance, slowing down as it goes, and this object does the same. What's important to note is that in that time, they will have reached exactly the same height. So we follow it still further and it's slowing down now, and this object does the same. We then come back and it finishes its flight to the top. This object does the same, reaching the same height. Now we turn back over and we start to fall, and the same thing happens here, falling a little bit, and this one does the same, and then it starts falling faster and faster until it hits the ground again, and this one does the same. What we can do now is use our one-dimensional mathematics to work out the time that this object takes to rise and then fall back to the same height again. And since the motion of the particle is going to end when it hits the ground, that's also the time that the object is moving horizontally. And since the object is moving at a constant horizontal speed, the total distance that this object has traveled is given by d equals UH times the time that we get from that vertical motion. And so this gives us a way to approach all projectile motion problems. In the vertical direction, it's acting under the effect of gravity, so it's accelerated motion. We use our motion laws to work out exactly how long that object is going to take to travel up, down, whatever it needs to do until it stops. We then use that time to calculate the horizontal displacement of the object, or the range that it's going to move in that time. What we're going to do now is take a look at an example. So we've got a little guy here standing at the top of a 180-meter high cliff, about to throw a rock from the cliff out into the water below. The rock will be thrown horizontally from the cliff at 3 meters per second. And we wish to know the distance d that the rock will fall into the water away from the base of the cliff. As always, we start by defining our positive directions. In this case, I've picked to the right as positive, and I've chosen to put positive as being down. The reason for this is that the direction of the acceleration and the direction of motion are both the same, and in this case downwards, which means it makes sense to make this the positive direction so that we don't have to worry about any negatives. I've also written out everything that I know, that the vertical displacement of the rock will be 180 meters, its acceleration will be 9.81 meters per second squared, its initial velocity will be 0. This is important because while the rock has an initial velocity of 3 meters per second, that is horizontal. Its vertical initial velocity is 0. And we wish to know the time it will take for the rock to drop. Remembering that the rock projected forwards and a rock that was dropped straight down the cliff would fall into the water at the same time. We start with our equation that s equals ut plus half at squared, and of course since u is 0, that will simplify to s equals half at squared. This gives us that 180 equals half times 9.81 times t squared. This gives us that t squared equals 36.7, and therefore the time taken for the rock to fall into the water is approximately 6.1 seconds. Now, during the time of its fall, the rock is moving with a constant horizontal velocity of 3 meters per second. Again, this is because there is no acceleration acting on the rock in the horizontal direction, because we're discounting forces like air resistance. What this means is that the distance traveled by the rock will simply be equal to its horizontal velocity multiplied by the time of its fall. Remembering that the time that the rock falls into the water will be the end of both its vertical and horizontal motion. This means that the distance is going to be equal to the 3 meter per second velocity of the rock horizontally multiplied by the 6.1 second time of fall that we've already calculated. And this gives us an answer of approximately 18 meters. Of course, if we're taking significant figures into account, 3 meters per second as the initial velocity of the rock only has one significant figure, so we would therefore have to state that we can only be certain of the distance away from the cliff to the nearest 10 meters. So in this case, we would say that it would fall approximately 20 meters away from the base of the cliff.